Alright, welcome back. Now we're picking up with 18.12, Occurrence, Preparation, and Properties of the Noble Gases, and that's what we're going to be discussing. This should be a pretty quick section. So all of our noble gases are present in the atmosphere in small amounts. They have very low boiling points and melting points due to the only intermolecular force that's present between them being very, very weak London dispersion forces. Helium itself is isolated by liquefying the condensable components of either natural gas, which leaves only gaseous helium behind. It is the only substance that is known that actually does not solidify with cooling at a normal pressure. It's used for filling balloons in aircraft and often mixed with oxygen tanks for high pressure water divers. So it's very important actually for that. It's also used for making inert atmospheres, which is often needed in laboratories or sometimes in welding. It's used as a liquid helium can be used as a coolant for cryogenic research and to get the low temperatures needed for superconduction. It might be used as a coolant for MRIs instead of liquid nitrogen. And there are actually no stable compounds of helium known. One thing with helium that I tend to be anti-helium balloons for, and that's because they don't really have much of a purpose. They might be kind of pretty, but they end up taking up a lot of the world helium supply, which is really needed in things like science labs. A lot of labs are having to find alternative sources of some type of inert carrier gas for their instruments, which is not easy, but a lot of it is due to the rising price and limited availability of helium. So I generally do not buy helium balloons. They may be pretty, but they have some issues. Save the helium. Okay. Come on, video. Keep going. Argon is produced by fractional distillation of liquid air. It's often used in light bulbs and is the third most abundant gas in dry air. It can form unstable compounds at low temperatures. So it has to be low temperatures, and the compounds it forms are pretty unstable. Neon is produced by fractional distillation of liquid air, kind of like argon. It is a component of neon lamps and signs, as many of us know. Not sins, signs. I will scribble that out. If you're an artist, draw what you think a neon sin looks like. There are no known stable compounds that contain neon. Krypton is produced by fractional distillation of liquid air. It's used potentially in krypton xenon flash tubes for high-speed photography. And it can form the difluoride KrF2, but this is thermally unstable at room temperature. Radon tends to come from radioactive elements as a product of radioactive decay. It is present in soils and minerals in low amounts, and it can actually be a health hazard because of this. So if you have a tightly sealed building that's well insulated, especially if it has a basement, argon can actually leach in from the ground, and when it's insulated and sealed, it can then accumulate as it continues to leach in and is a potential carcinogenic. So it's worth it if there's like a building that seems to, be very well insulated and has a basement, to periodically check argon levels. There is evidence of it forming RnF2, so fluorine being like the only thing that can form compounds with it. And then we have xenon, which is produced by fractional distillation of liquid air, and it can actually form stable compounds with fluorine. Depending on the stoichiometry, after heating excess xenon gas with fluorine gas, we can form a difluoride, a tetrafluoride, or hexafluoride. If you take xenon hexafluoride and react it with water, you can form a xenon trioxide solution that puts xenon in its 6+ oxidation state. If you were to take this xenon trioxide and have it very dry, it's explosive and can spontaneously detonate. So that's fun. The xenon hexafluoride and xenon trioxide can both undergo disproportionation when they're put in a basic solution, and this will produce xenon gas, oxygen gas, and salts of the perxenate ion, which is Xe064-. And in this ion, xenon actually has a maximum oxidation state of 8+. It's kind of crazy, right? Okay, so where am I? Come on, start writing the reaction. Okay, so when we take that xenon hexafluoride, just to show you the reaction, it's a solid, we put it in water, and it will form the xenon trioxide. So this is that reaction I'm talking about, which is aqueous. So it's not dried yet, so it won't spontaneously detonate until we dry it. And it also forms hydrofluoric acid. And with that, that ends chapter 18. Finally, we did it. I am so sorry about how much this chapter sucked, you guys, but I hope maybe there were some things that were kind of interesting for you. I know it was a lot of talking and like no math. It's just stuff to know and memorize, and I apologize. But we'll get through it. We're almost done. We only have 2 more chapters left in the book. We're almost done. As usual, if you guys need any help, please reach out and know that I am here for you. I'll see you soon.